Imagine you are just cruising down the highway. You know, you're in a modern hybrid vehicle,
hmm
just enjoying the smooth ride. You've got your coffee, maybe some music playing.
Sounds like a pretty ideal morning, honestly.
Yeah, right. But underneath you, completely out of sight and, out of mind, the electric traction motor is spinning at a blistering 12,000 revolutions per minute.
Which is an absolute powerhouse of a machine.
Yep.
Just generating massive torque, perfectly synced with the road.
Exactly. But then, inside that motor, hidden beneath heavy layers of steel, resin, and insulation, a single critical wire snaps.
Just a sudden, catastrophic mechanical break in the winding. And this is happening while immense amounts of power are, actively flowing right through it.
So what happens next? Like, does the car instantly lock up at 70 miles an hour? Does the high-voltage battery just overcharge and fry itself in a spectacular shower of sparks under your seat?
I mean, it's a terrifying scenario when you think about it,
Yeah.
especially when you start doing the math on the sheer amount of electrical and physical energy moving through a powertrain at highway speeds.
It's a massive amount of kinetic energy.
It really is. And without layers of incredibly sophisticated protection, that single snapped wire would absolutely lead to a total system failure. The physical forces involved are just, they're too extreme to fail gracefully on their own.
Well, welcome to today's Deep Dive. We are taking a fascinating and honestly mind-blowing look into a highly technical engineering architecture today.
Yeah, we have some really incredible source material to go through.
We do. Our focus today is on a highly detailed five-dimensional engineering blueprint. It covers the functional safety and fault diagnostics for what they call motor winding open circuits and hybrid dual motor power control systems.
It sounds like an incredibly dense subject, and on paper, it definitely is.
Oh, for
We are dealing with functional safety frameworks, specialized metallurgy, advanced vector calculus.
yeah, the heavy engineering stuff.
Right. But when you peel back the jargon, this is essentially a survival guide. It is a masterclass in how human engineers anticipate, detect, and neutralize extreme physical violence happening inside a machine.
Because this isn't just a story about a wire breaking. Getting into the details of these systems made me realize this is basically a microscopic war zone.
That's a really good way to put it.
We are talking about thermal overloads that can literally melt copper, invisible arcs of electricity acting like miniature lightning strikes, and software reflexes that have to diagnose the problem and intervene in mere milliseconds to save your life.
That's a real race against physics.
It really is. So we are going to unpack the sheer brilliance of how this all works. For you listening, we're going to break down all 5 dimensions of this technical spec so you can really appreciate the invisible shield keeping you safe on the road.
I think a really good place to start is the origin of the failure itself.
Mm-hmm.
We need to understand the environment that causes a heavy-duty copper wire to fail in the first place.
Because it's not just standard wear and tear.
Right, no, not at all. It requires a perfect storm of environmental hostility.
Let's unpack that. Because before we look at how the car's brain saves the day, we have to look at the anatomy of the break. The materials we are looking at outline 3 distinct root causes for this kind of open circuit failure.
Right, the motor body faults.
Exactly. And the first one is mechanical fatigue. And to understand this, you really have to picture the chaotic environment inside that motor casing.
You really do. Picture the mechanical resonance. When a traction motor is operating under heavy load, it generates these intense, high-frequency random vibrations.
It's like a really intense buzzing.
Yeah, exactly. The magnetic forces pulling and pushing on the stator teeth cause the entire structure to hum and vibrate violently, typically at resonance frequencies between 100 hertz and 1000 hertz.
That is essentially an acoustic vibration. Like the physical metal is vibrating so fast, it's practically generating sound waves.
It is. Now take that high-frequency vibration radiating from the core of the motor and stack it on top of the low-frequency vibrations coming from the chassis.
You mean like the shocks and jolts as you drive over potholes or, uneven pavement?
Exactly. You end up with this highly complex, multi-directional matrix of mechanical stress. And then we have to add temperature into this equation.
Right, because motors get hot.
Very hot. The environment inside the motor swings wildly. It could be soaking at negative 40 degrees Celsius after sitting outside in a freezing winter night.
Wow.
And then it can just rocket up to positive 150 degrees Celsius after just a few minutes of heavy highway acceleration.
So if I'm picturing this correctly, it's like trying to bend a thick paper clip back and forth until it snaps. But you're doing it while bouncing on a trampoline inside a blast furnace?
I love that. That is a remarkably vivid and accurate analogy. Metal fatigue happens at the crystalline level, you
The
see.
crystalline level.
Yeah. When the copper wire, specifically the heavy enameled wires forming the stator windings, is constantly expanding from the intense heat and contracting from the cold, while simultaneously being violently shaken in multiple
I
directions.
just can't handle it.
Right? The crystalline structure of the metal begins to form microscopic slip bands. And over millions of cycles, these slip bands turn into micro cracks at stress concentration points.
Like the neutral point welds, or the spots where the delicate windings have to connect to the rigid, high-voltage copper bus bars.
Exactly. Those connection points are the prime targets. The rigidity of the bus bar fights against the vibration of the winding, and eventually the fatigued metal simply gives up and fractures.
That covers the physical shaking. But there is a second failure mode in the source material that feels like a completely different kind of violence. Thermal overload and melting.
Yeah, this one is brutal.
This isn't about the wire getting tired, right? This is about the wire literally turning to liquid.
Right. Thermal overload occurs when the vehicle's limits are pushed beyond the cooling system's capacity. Imagine a heavy-duty hill climb towing a trailer, or a driver doing, repeated rapid accelerations.
Pushing the car to its absolute limits.
Exactly. During those events, massive amounts of phase current are forced through the stator windings. As the current increases, you get intense localized joule heating.
Oh, I remember reading about this. I squared R heating, right? The heat goes up exponentially with the current based on the natural resistance of the copper wire itself.
You've got it. The exponential factor is what catches systems off guard. Under normal conditions, the liquid cooling jacket surrounding the motor absorbs this heat and carries it away.
Okay, so normally it's fine.
Right. But what happens if the cooling channels are partially obstructed? Or, more commonly, what if there is a microscopic breakdown in the insulation between two adjacent loops of wire inside the motor?
Oh, the interturn short circuit they mentioned in the spec?
Yes, the interturn short. When two turns of the winding touch, it creates a localized loop that basically bypasses the main circuit. The magnetic field induces massive, unintended circulating currents inside that tiny little loop.
Because the resistance dropped.
Exactly. And the heat generation skyrockets in a matter of milliseconds.
I noticed a specific temperature threshold mentioned in the engineering specs, the Class H temperature limit of 200 degrees Celsius.
Right. Automotive traction motors typically use Class H insulation. The synthetic enamel coating on the wires, the resin binding them together, and the copper itself are rated to survive continuous operation up to 200 degrees.
Which is already incredibly hot.
It is. But when an interturn short happens, or the cooling fails during a massive torque request, the heat generation violently outpaces the cooling dissipation. The temperature blasts past 200 degrees, the insulation vaporizes into carbon,
And the physical copper wire hits its melting point.
yes, it liquefies, parts ways, and creates a hard open circuit.
The idea of temperatures getting that high, that fast, inside a component sitting just a few feet away from you while you're driving is intense.
It's definitely something you don't want to happen.
But the third cause of failure is where things get really fascinating to me because it sounds almost impossible. It's called micro-earthing and interfacial damage.
Ah, yes, the micro-earthing.
The data shows this entire failure cascade can be triggered by microscopic movements of less than 5 micrometers. I mean, I need you to help me wrap my head around this. Less than 5 micrometers is smaller than a red blood cell.
It is incredibly tiny.
How does something moving less than a red blood cell destroy a piece of heavy machinery?
Well, the physics of fretting wear are incredibly destructive. Let's look at the connection points, the metal pins and sockets where the high-voltage cables plug into the motor.
Okay, the main plugs.
Right. Even if they are bolted tightly, the intense vibration we discussed earlier can cause those metal surfaces to slip against each other by just 5 micrometers.
So to the naked eye, it looks perfectly solid.
Exactly. To the naked eye, the connection looks perfectly still. But at the microscopic level, those metallic peaks and valleys are aggressively rubbing together.
And that tiny, invisible scraping is enough to damage the protective plating on the pins.
It scrapes it away completely over time. When the protective plating is gone, the raw, bare copper underneath is exposed to the air. And at elevated motor temperatures, bare copper oxidizes incredibly fast.
It basically rusts.
Yes. This metal oxide, essentially copper rust, begins to build up in those microscopic valleys on the surface of the pin.
But metal oxide isn't a conductor, is it?
No, it is a strong insulator. So you have a connection point that is supposed to have a baseline electrical resistance of less than 5 milliamps. It is designed to let hundreds of amps of current flow freely.
But now there's this crust in the way.
Right. As that insulating oxide layer builds up, the electrical resistance at that tiny connection point skyrockets exponentially.
You essentially create a bottleneck. You have a massive current trying to just, push its way through a tiny spot that suddenly refuses to let it pass.
The pressure builds, and as the microscopic vibration continues, there will be a fraction of a millisecond where those two oxidized contacts momentarily separate.
Just a microscopic gap.
The gap might only be a few micrometers wide, but because the electrical pressure, the voltage is so high, and the current has nowhere else to go, it breaks through the air gap. It ionizes the air and creates a microarc.
Like a miniature lightning strike inside the connector.
Precisely. A highly localized plasma channel. And plasma is exceptionally hot. We're talking thousands of degrees in a space the size of a pinhead.
Wow.
These microarcs possess extremely high energy density. The moment the arc strikes, it instantly melts the surrounding metal on the pins, carbonizes the plastic connector housings, and fundamentally destroys the metallurgical structure of the joint.
It just nukes the whole connection.
It does. The connection goes from slightly resistive to completely obliterated in a flash, resulting in a sudden, permanent open circuit.
So we have three incredibly violent ways this can play out. The wire gets physically shaken until it cracks, it experiences a thermal runaway and melts from the inside out, or it gets blown apart by microscopic plasma lightning caused by a 5-micrometer vibration.
It's a terrifying anatomical breakdown of a failure for sure.
But that brings us to the next massive challenge in the blueprint, the technical architecture and software diagnostics. Physics has taken its course. The wire is broken. Now the clock starts.
Right, the transition from the physical realm of metallurgy to the digital realm of software algorithms happens in the blink of an eye.
Because the car's computer system has to somehow realize a wire has snapped before the electrical backlash destroys the entire vehicle.
Exactly. When a high-voltage winding suddenly opens while a motor is spinning at 12,000 RPM, the electrical dynamics shift from controlled power delivery to highly volatile, uncontrolled chaos.
And there is a strict timeline the computer has to beat. The functional safety architecture, which is governed by the ASIL-D standard, dictates a 60-millisecond rule.
Yeah, ASIL-D. That represents the highest classification for automotive hazard risk. It is reserved for systems where a failure could lead to life-threatening fatal injuries.
Like suddenly losing steering on the highway.
Or in this case, sudden, violent loss of propulsion and a potential battery fire. Under ASIL-D, this specific motor control system has a fault-tolerant time interval, known as the FTTI, of less than or equal to 60 milliseconds.
Meaning the car's brain must detect the broken wire, process what that means, decide on a course of action, and physically trigger the safety hardware to intervene.
All in less time than it takes a human being to blink.
If the system takes 61 milliseconds to intervene, what happens?
Well, the unmitigated voltage spikes could punch right through the inverter's delicate silicon carbide transistors. They'd blast into the high-voltage direct current bus and severely damage the battery pack.
That's where the fire risk comes in.
Exactly. Or the sudden asymmetrical magnetic field in the motor could cause a violent torque shear that could potentially snap the drive shaft or throw the vehicle into a spin. The system just has to be faster than the physics of the disaster.
So how does software detect a physical break that fast? It's not like there's a tiny camera inside the motor watching the wire.
No, it relies on a couple of deeply clever diagnostic algorithms. The first one is called the current residual check, which operates on Kirchhoff's current law.
Okay, KCL, walk me through that.
Kirchhoff's current law, or KCL, is a fundamental principle of electrical circuits. It basically states that the total current entering a junction must equal the total current leaving it. Energy cannot just vanish.
Makes sense.
In a healthy, three-phase alternating current traction motor, the currents flowing through the three massive cables labeled phases A, B, and C are perfectly balanced sine wave alternating currents.
So they're constantly shifting up and down, but they are totally synchronized.
Exactly. The field-oriented control software, which is the brain of the inverter, constantly monitors the exact amperage in phases A, B, and C using high-speed sensors. The software algorithm continuously adds those three values together.
It's a simple addition.
Simple addition. Because of how three-phase power works, when you add the instantaneous current of A plus B plus C together at any given microsecond, they perfectly offset one another. The sum is always mathematically zero.
Or, very close to zero, factoring in a tiny bit of acceptable sensor noise.
right? The mathematical harmony, it's basically constant. But the exact instant a wire snaps in, say phase A, the current flowing through phase A drops to absolute zero. It has nowhere to go.
Oh, I see.
Suddenly, when the computer calculates the sum of A, B, and C, it no longer equals zero. The sum wildly deviates. The fundamental law of the circuit is broken.
And how fast does the software catch that deviation?
The field-oriented control algorithm is designed to catch this mathematical deviation in just 2 milliseconds.
2 milliseconds to realize the physics don't add up. That is unbelievably fast.
It is remarkably fast, but speed introduces its own problems.
What do you mean?
If you only rely on the KCL check, a random burst of electromagnetic interference from, say, a cell tower, or just a temporary glitch in a current sensor, could cause a mathematical imbalance for a couple of milliseconds.
Oh, a false positive.
Right. If the car instantly shuts down the highway propulsion every time a sensor glitches, you create a new, massive safety hazard. You can't have false positives when you're dealing with life-critical systems.
So it needs a second opinion.
Exactly. Therefore, the architecture requires confirmation. The system uses a secondary parallel diagnostic called PI saturation detection to verify the open circuit.
Okay, this is where I need you to slow down and walk me through the math, because this part of the engineering blueprint really made my brain hurt.
It gets a bit abstract, yeah.
It talks about DQ-axis PI controllers. I mean, I'm picturing a standard XY graph from high school algebra, but we're talking about a spinning three-dimensional magnetic cylinder inside a motor. What is a DQ axis, and what is the computer actually looking at?
It is one of the most brilliant mathematical tricks in modern engineering. Trying to control three alternating currents that are constantly changing, constantly swinging up and down in a 3D spinning motor is mathematically exhausting for a computer.
Just too much data to track in real time.
Right. So engineers use something called the Clark and Park transformations.
A mathematical translation.
Exactly. These mathematical formulas take the three complex spinning AC currents and map them onto a flat, two-dimensional coordinate system that spins at the exact same speed as the motor's magnetic field.
Okay.
This new 2D plane has two axes. The D-axis, which controls magnetic flux, and the Q-axis, which controls the torque. By shifting to this spinning frame of reference, those wild alternating currents suddenly look like flat, steady, direct currents to the computer.
Oh, wow. So instead of trying to hit a moving target, the computer just locks onto the target and spins with it. It radically simplifies the math.
It simplifies the math so the PI controllers can do their job. PI stands for proportional integral. Think of the PI controller as the cruise control for the electrical current.
Okay.
The driver presses the accelerator, demanding a specific amount of torque. The PI controller looks at the target current it needs on the Y-axis, looks at the actual current it is currently getting, and adjusts the voltage to make them match.
Got it. So the wire breaks. The current drops to zero. How does the PI controller confirm the break?
Well, when the current drops to zero, the PI controller doesn't possess artificial intelligence. It doesn't instantly know the wire snapped. All it knows is that there is a massive error between the current it wants and the current it is getting.
Right.
So it relies on its integral mathematical function.
I was trying to come up with an analogy for this because at first I thought of it like flooring the gas pedal, but that doesn't really capture the integral part, the buildup of the error over time.
The gas pedal is proportional. You push it, it goes. The integral part requires a different visualization.
What if we think of it like a massive water dam?
Okay, let's hear it.
The controller opens a valve, expecting a certain flow of water or current to come out the other side. But the pipe is broken, so no water is flowing. The controller sees this error, and the integral math starts piling up that error over time, like water rapidly filling up a reservoir behind a dam. The longer the water doesn't flow out the pipe, the higher the pressure builds behind the dam as it desperately tries to force the flow.
That is a phenomenal analogy. The mathematical error accumulates incredibly fast. The PI controller takes this building pressure and cranks its output voltage duty cycle higher and higher, trying to push electricity across the broken gap.
But the gap is broken, so nothing happens.
Exactly. Within a fraction of a millisecond, the pressure hits the top of the dam. The controller maximizes its voltage output to 100%. It can't push any harder. It becomes mathematically saturated.
It's giving it absolutely everything it has.
If the controller stays absolutely saturated at 100% for greater than or equal to 1.1 milliseconds, while the return current remains totally flat at zero, the microcontroller verifies the reality.
It cross-checks its work.
Right. It looks at the current residual check, which says the math is broken, and it looks at the PI controller, which says the dam is overflowing and no current is moving.
And that confirms it.
It cross-references these two independent logic paths, confirms the hard open circuit, logs the severe fault code, and immediately kills the high-voltage switch signals to the motor.
And all of this complex vector calculus, error accumulation, and cross-checking happens in about 2 milliseconds.
It's credible. And this speed and reliability is achieved through a Dewar-Checker hardware architecture.
What does that mean, practically?
The primary processor running these safety systems is a specialized dual-core microcontroller. One processing core is actively running the motor control calculations, doing the math, while the second independent core is strictly monitoring the first core's outputs, checking the math.
Ah, the doer and the checker.
Exactly. It is a highly orchestrated, redundant verification process where analog hardware sensors and software algorithms cross-examine each other to confirm a physical reality well within that critical 60-millisecond window.
It is genuinely incredible that humanity has designed logic gates that can think and act that fast. But here's the terrifying part of the blueprint, and this brings us to the third focus area, the hardware degraded states, the ultimate safety net.
Because turning off the switches isn't the end of the story.
Right, because even though the software brilliantly realized the wire is broken and cut the power, the physical car is still rocketing down the highway. The motor is still physically spinning at 12,000 RPM.
The momentum of a 2-ton vehicle doesn't just disappear in 2 milliseconds.
Yeah.
And that spinning magnetic rotor is suddenly the greatest threat to the vehicle.
How so?
Because an electric motor is fundamentally identical to an electrical generator. When you spin permanent magnets inside coils of copper wire, you generate electricity.
It's basically the basic principle of a wind turbine.
Precisely the same principle.
Yeah.
In automotive engineering, this generated voltage is called back EMF, or back electromotive force. Normally, the battery voltage pushes against this back EMF to drive the car forward.
But the battery is disconnected now.
Right, because the safety system just cut the drive signals to protect itself from the broken wire. There is suddenly massive uncontrolled energy being generated by the spinning magnets with nowhere safe to go.
The motor just becomes a rogue generator pumping out high voltage. So how does the system handle that without frying the electronics?
The engineering specs outline two completely different hardware strategies depending on the physical architecture of the motor.
The first one applies to multi-phase or dual winding systems. And I have to say, this is one of the most elegant engineering solutions I've ever encountered in these blueprints.
It really is brilliant.
It details repurposing the broken winding into a redundant search coil. I mean, how does a broken piece of metal become a sensor?
It is a profound example of dynamic resourcefulness. In a high-performance dual-winding system, you essentially have two complete independent sets of motor windings woven together inside the stator, and they're powered by two separate inverters.
Okay, so a backup system is built in.
Right. When the software detects the hard open circuit in one set of windings, it immediately suspends that entire half of the system. It shuts down the drive bridge for the broken side.
So that damaged half of the motor is just completely dead in the water. No power going in.
It is depowered, yes.
Yeah.
But it is still physically sitting inside the motor, surrounding the spinning magnetic rotor.
Oh, I see where this is going.
The system then relies on the healthy secondary winding to keep the vehicle stabilized. It limits the output of the healthy winding to about 30% of maximum torque, just enough power to let the driver safely pull over to the shoulder or limp home.
But the true genius is what the computer decides to do with the broken suspended winding, right?
Exactly.
Okay.
Because it's no longer being used to drive the car, it's just sitting there absorbing the magnetic field. Because no drive current is being pumped through that broken winding, there's no switching noise, no high-frequency interference from the inverter.
It becomes perfectly quiet, electrically speaking.
The software instantly reconfigures its logic to treat the broken winding as a highly sensitive physical search coil. The spinning magnets generate pure back EMF voltage on those broken terminals, and the computer just measures this pure voltage sine wave.
It just listens to the broken wire. That is wild.
By measuring the amplitude and frequency of that clean voltage signal, the computer can calculate the exact physical angle and rotational speed of the spinning rotor.
Why is that better than the normal sensors?
Usually, sensorless control relies on complex, easily confused mathematical estimators that have to constantly compensate for temperature drift and magnetic saturation. By using the broken winding as a dedicated sensor, the system gains a flawless real-time data stream of the motor's internal state.
That is recycling at its absolute finest. The exact component that caused the catastrophic failure becomes the precise instrument the car uses to safely navigate the aftermath.
It guarantees an incredibly stable and robust limp home mode, ensuring you maintain steering and propulsion without risking further damage.
But what if you don't have a high-end dual-winding motor? Like, what if you were driving a more standard hybrid with a single-winding motor and no redundancy?
That's the more common scenario.
If that wire snaps, you have zero drive power. The document says the system must execute a stepwise active short circuit, or ASC. Now, I have to challenge this logic because as a layperson, short-circuiting is the exact thing that causes electrical fires.
It definitely sounds wrong.
If you rub two battery terminals together, you get sparks and heat. You're telling me the official mathematically calculated safety protocol is to intentionally short-circuit the high-voltage motor while driving at highway speeds?
It is entirely counterintuitive.
Hmm?
To intentionally command a short circuit sounds like an act of sabotage. But in this scenario, you have to choose the lesser of two extreme physical evils.
Okay, what's the other evil?
If you simply shut off the inverter and let the motor spin freely, what engineers call freewheeling, that uncontrolled back EMF voltage will rise linearly with the speed of the motor.
Right.
At 12,000 RPM, that voltage will rise so high it will physically punch backward through the inverter's anti-parallel diodes.
Like a high-pressure water pipe bursting.
Exactly like that. It will blast into the high-voltage direct current bus and forcibly overcharge the battery pack.
And lithium-ion batteries do not like that.
They do not tolerate massive, uncontrolled voltage spikes at all. They will experience thermal runaway and catch fire. Furthermore, the voltage will exceed the breakdown limits of the delicate silicon carbide transistors in the inverter, permanently destroying them.
So, letting the energy escape the motor is a guaranteed catastrophic failure. You basically have to stop that energy from reaching the DC bus and the battery.
The only way to stop it is to trap the magnetic energy inside the motor itself. This is the active short circuit.
How does that actually work?
If the car is traveling at high speed, typically greater than 80 kilometers per hour, the microcontroller uses the exact rotor angle and current measurements from the millisecond before the break occurred. It dynamically calculates the optimal combination of transistor switches to close.
It orchestrates the short circuit in a very specific sequence, right? The stepwise execution they mentioned.
It cannot just slam all the switches shut instantly.
Hmm.
The initial transient electrical shock would be too violent. It could actually snap the rotor shaft.
Yikes.
So it executes a two-phase short circuit, or 2 PSC, for just a fraction of a millisecond. This absorbs the initial violent inductive kickback. Then, precisely 1.5 milliseconds later, it closes the remaining switches, transitioning into a full three-phase short circuit, or 3 PSC.
Walk me through the physics of that. What happens when you short all three phases together?
By intentionally shorting the phase terminals together at the inverter, you create a closed loop. The spinning magnetic field induces massive current inside the stator windings, but because they are shorted, the current just circulates endlessly within the motor's own massive copper coils and iron core.
So it's trapped.
Right. The magnetic field created by the short-circuit current physically opposes the magnetic field of the spinning rotor. They fight each other, trapping the energy locally.
It's like an electromagnetic cage. The energy is forced to stay inside the heavy metal of the motor instead of shooting backward into the delicate electronics.
It is a calculated strategic sacrifice. You are intentionally generating massive amounts of heat inside the motor, sacrificing efficiency, and potentially slightly degrading the motor's lifespan.
But the trade-off is worth it.
Absolutely.
Yeah.
You do it to achieve absolute, immediate safety for the rest of the vehicle.
Yeah.
The safety data confirms this action successfully clamps the DC bus voltage to a safe level, keeping it strictly below 720 volts.
Why 720 volts specifically? Like, what happens at 721?
It comes down to component safety margins. The advanced silicon carbide, or IGBT power modules in modern hybrid inverters are often rated for a breakdown voltage of around 900 to 1200 volts.
Okay.
However, the battery architecture usually operates around 400 to 800 volts. Clamping the runaway voltage firmly below 720 volts provides a mathematical safety buffer.
A cushion.
Right. It guarantees that the voltage remains high enough to circulate the trapped energy, but low enough that it will never punch through the transistor gates or trigger a chemical reaction in the battery cells.
And what if this happens in city traffic? Say you are driving under 20 kilometers per hour when the wire snaps. Do you still short circuit?
No, at low rotational speeds, the physics change. The spinning magnets simply aren't moving fast enough to generate a back EMF voltage that exceeds the battery voltage.
So the electrical pressure is too low to punch backward through the diodes.
Precisely. In this specific low-speed scenario, the system executes the freewheeling state. It just shuts off all the gate signals entirely, safely letting the motor's torque smoothly drop to zero. The driver simply coasts to a stop without any dramatic electrical interventions.
Okay, let's take a breath and recap where we are. We've seen how the failure happens, we've seen how the 2-millisecond software catches the brake by monitoring the math, and we've seen how the hardware physically traps the explosive energy or repurposes the broken wire to keep the car stable.
It is a brilliant orchestration of survival.
But for an engineer, surviving a catastrophic failure is only half the job. And this brings us to the fourth dimension of the blueprint. The real victory, the true engineering flex, is ensuring the failure never happens in the first place.
Yes. This moves us into the realm of predictive engineering. How do you design a physical system that defies the chaotic laws of physics?
This is the domain of DFMEA, right? Design failure mode and effects analysis.
Exactly. The engineering teams take the root causes. We discuss the violent vibration, the thermal melting, the microarcing, and they physically alter the metallurgical and structural design of the motor to neutralize those threats long before the car is ever built.
I was looking at the section on mechanical fatigue, the problem with the vibration tearing the metal apart. The manual mandates a massive physical upgrade. They require strain relief brackets at every critical junction.
The fundamental philosophy here is isolation. You cannot stop the massive rotor from generating intense vibrations. It is an inherent byproduct of generating torque.
Right, the motor is going to shake.
But you can sever the mechanical pathway that allows that vibration to reach the fragile welds and connections. The mandate requires specialized, mechanically tuned brackets at all high-voltage terminals.
How do they work?
These brackets act as microscopic shock absorbers. They are tuned to dampen the specific resonance frequencies of the motor.
So they act like a filter for the physical shaking.
A highly effective filter. The design specification is incredibly strict. These brackets must limit the high-frequency vibrational movement at the actual contact points to less than 10 micrometers peak to peak.
That is profound. The entire motor might be shaking violently enough to rattle your teeth, but by the time that kinetic energy travels through the bracket to the fragile weld, it has been reduced to a shimmy of less than 10 micrometers.
You fundamentally engineer the mechanical stress out of the system. The copper no longer flexes, meaning the slip bands never form, meaning the microcracks never develop. You cure the metal fatigue before it begins.
That solves the gross mechanical failure. But earlier, we talked about the microarcing, the miniature lightning strikes.
Right, the fretting wear.
You mentioned that just a 5-micrometer slip was enough to scrape off the plating, expose the bare copper, create oxidation, and start the lightning storm. Even with the strain relief brackets limiting movement to 10 micrometers, that is still double the movement needed to trigger the microarcing. How do they stop the microscopic friction?
This requires a radical transition in material science. Mechanical brackets aren't enough. You must change the fundamental metallurgy of the connection.
So what's the change?
The engineering blueprint entirely bans the use of standard tin-plated brass for these critical terminals. Brass is cheap and easy to machine, and tin plating is standard in most consumer electronics.
But not good enough for this.
No. Under harsh automotive vibrations, tin oxidizes far too aggressively.
So they throw out the cheap metal. What replaces it?
They upgrade the base terminal material to a specialized alloy called beryllium copper, often referred to as cube.
Beryllium copper. I know beryllium is heavily used in aerospace and satellites. It has to be significantly more expensive than standard brass.
It is exponentially more expensive and far more difficult to machine.
Yeah.
But beryllium copper possesses a unique metallurgical superpower. Precipitation hardening.
What does that mean for the connector?
It boasts incredibly high tensile strength and elasticity, meaning it acts like an indestructible spring. Most importantly, it retains that massive spring force even when subjected to continuous 150 degrees Celsius temperatures. It never relaxes its grip on the connection.
But it's still copper. Won't it still oxidize and create that insulating layer if it rubs?
Not if you completely encapsulate it. And this is where the materials get truly exotic. They take this high-strength beryllium copper and electroplate it with a dense nickel barrier layer.
Okay, a nickel base.
Then over the nickel, they apply a heavy plating greater than or equal to 1.27 micrometers thick of what is specifically designated as soft gold.
Soft gold. Is there a difference between that and the gold in, like, a wedding ring?
A massive difference. Jewelry gold is usually alloyed with silver, copper, or zinc to make it hard and durable so it doesn't scratch. Soft gold is essentially pure, unalloyed gold.
Why use that?
In electrical engineering, gold is coveted because it is highly conductive, but its true value is its nobility. Gold is a noble metal. It absolutely refuses to react with oxygen. It does not rust, it does not tarnish, it does not form insulating oxides.
So it solves the oxidation bottleneck entirely.
It solves the oxidation, but the softness is the true mechanical trick. Soft gold is highly ductile. When two soft gold-plated terminals vibrate against each other at the microscopic level, the gold doesn't scrape, fracture, and tear like tin or hard metals.
What does it do?
It smears. It acts as a solid-state dry lubricant.
That is fascinating. The metal lubricates itself.
The surfaces glide smoothly over one another. Because the gold doesn't oxidize and because it lubricates the friction point, there is zero insulating buildup. The electrical resistance remains flawlessly flat forever. It completely prevents those black spots of friction oxidation from ever taking root. By eliminating the microscopic resistance spike, they completely neutralize the conditions required for microarcing. They use material science to mathematically forbid the lightning strike.
That is an incredible application of chemistry to solve a mechanical problem. But the physical shape of the connection changes too, doesn't it? The DFMEA specifies a shift away from standard flat pin connectors to something called a hyperboloid basket topology.
Yes, standard high-power connections often rely on a flat, solid pin sliding into a flat split sleeve. It is a friction fit.
Pretty standard stuff.
But in a high-vibration environment with intense G-forces, a flat surface can momentarily chatter. It can bounce apart for a microsecond. The hyperboloid contact completely re-engineers the geometry of the connection to ensure that never happens.
I was trying to visualize this hyperboloid shape, and I think I've got a good analogy.
Let's hear it.
A standard flat connection is like a high five. Two flat hams pressing together. If someone bumps your arm hard enough, the hands separate instantly, breaking the connection.
Right.
But a hyperboloid basket is like a woven finger trap. The female end of the connector isn't a flat sleeve. It's a cage made of dozens of precisely angled, spring-loaded wires. You push the solid pin inside, and these spring wires wrap around it and twist, gripping it from all 360 degrees.
That perfectly describes the mechanics of it. The engineering goal is redundancy at the microscopic level. The hyperboloid cage provides between 10 to 20 parallel points of independent mechanical contact.
So there's always a backup.
Exactly. If an extreme violent shock from a pothole causes one or two of those microscopic wires to momentarily lift off the pin, the other 18 points are still holding tight, anchored by the spring force of the beryllium copper.
No matter how violently it shakes, something is always touching.
They maintain perfect, uninterrupted electrical continuity. It completely prevents those momentary microsecond disconnects that would trigger a fault code in the software.
It really highlights the uncompromising nature of these safety standards. I mean, machining beryllium copper, electroplating it with pure soft gold, and weaving complex hyperboloid cages. The manufacturing cost per vehicle must be staggering compared to standard brass pins.
Cost optimization is always a priority, sure, but when an engineer is designing an architecture to meet ASIL-D safety requirements, cost fundamentally takes a backseat to reliability.
The stakes are just too high.
You are guaranteeing that a family driving down the highway at night will not suddenly lose propulsion. Eliminating the microscopic root causes of fatigue and friction oxidation is not an optional luxury. It is a mathematical prerequisite to achieve the safety target.
Okay, so the design engineers have done their job perfectly. The blueprint dictates a gold-plated, shock-absorbing hyperboloid connector that defies physics. It is flawless on paper.
On paper, yes.
But here is the next massive hurdle and our fourth focus dimension, the PFMEA. You can design the perfect component, but if it is put together incorrectly on a loud, busy assembly line by a tired worker or an uncalibrated machine, it will still fail.
Absolutely.
How does the factory ensure absolute unyielding perfection during assembly? Because humans and mass production machines make mistakes.
The transition from perfect theory to perfect reality is governed by the PFMEA, process failure mode, and effects analysis. The manufacturing engineers have to control the assembly environment as strictly as the design engineers control the metallurgy.
And one of the most aggressive steps they take is targeting the most common source of variation on an assembly line, the pneumatic torque wrench.
Oh, yeah. They don't mess around with those.
I found this detail fascinating. The process manual completely bans the use of standard pneumatic air guns for these high-voltage connections. I've been in factories and air guns are everywhere. Why are they suddenly the enemy?
A traditional pneumatic air gun is a blunt instrument. It uses air pressure to hammer a bolt until a mechanical clutch slips, indicating it feels tight. But feeling tight is not good enough for high-voltage bus bars carrying hundreds of amps.
So what do they use instead?
The PFMEA mandates the exclusive use of closed-loop torque angle servo screwdrivers. These are highly advanced robotic tools that don't just measure the twisting force. They precisely measure the exact degree of rotation of the bolt as it stretches the metal threads.
They measure how much the bolt is actually clamping down, not just how hard it is to turn.
Precisely. And they pair this robotic precision with something called OCR, optical character recognition.
This is where the process control becomes incredibly rigorous. Before the servo robot is even allowed to attempt driving the bolt, an OCR camera scans the specific bolt as it comes down the automated feeder.
It is. The camera is verifying via part numbers and visual finish that the bolt has a specific phosphate coating applied to its threads.
Why does a coating on a standard bolt matter so much that they need a camera to verify it?
Because of the tribology, the physics of friction.
Mm-hmm.
If a bolt is bare, uncoated steel, the friction of the metal threads grinding together as it tightens will eat up almost all the twisting force applied by the robotic screwdriver.
Oh, I see.
The tool will hit its torque target and stop, thinking it has clanked the joint perfectly. But in reality, all that twisting energy was wasted overcoming thread friction. The actual clamping force, the axial preload, holding the high-voltage metals together, will be dangerously loose.
And as we know, a loose joint vibrates, oxidizes, heats up, and eventually melts the winding.
Exactly. The phosphate coating acts as a highly consistent thread lubricant. It guarantees a uniform coefficient of friction across thousands of bolts. It ensures that when the robot applies 10 newton meters of torque, it results in the exact same microscopic clamping pressure every single time.
It is stunning to realize that a missing invisible coating on a 10-cent bolt can lead to a melted motor winding years down the road.
It's all connected.
But the factory controls go much deeper than just the bolts. The source material outlines the insulation process for the stator, which uses vacuum pressure impregnation, or VPI, followed by 3D AOI scanning. I'm going to be honest, this sounds more like the protocol for building a deep space satellite than a car motor.
The cleanliness and precision are definitely aerospace grade. Once the copper windings are perfectly assembled and welded inside the steel stator core, they have to be electrically insulated and structurally stabilized.
And they use the VPI for that.
Right. They use vacuum pressure impregnation. The massive, heavy stator is lowered into a sealed steel chamber. Massive industrial pumps suck all the air out of the chamber, creating a near-perfect vacuum. Then, they flood the chamber with a specialized, highly viscous, high thermal conductivity epoxy resin.
Why go through the trouble of creating a vacuum? Why not just dip the motor in a vat of resin, like dipping a candle in wax?
Well, capillary action isn't strong enough. The copper wires in a modern stator are packed together incredibly tightly. If you just dipped it in resin at normal atmospheric pressure, the air trapped deep inside those microscopic gaps between the wires would push back against the thick epoxy.
It wouldn't coat everything.
The resin wouldn't penetrate. By pulling a hard vacuum first, you remove the air entirely. When the resin is introduced, it is drawn deep into every microscopic crevice, completely encapsulating every millimeter of copper.
It seals the wires in a solid, impenetrable block.
They then bake the stator to cure the epoxy into a rock-hard solid. But the process control dictates that they cannot simply trust that the vacuum worked.
Hence the 3D scanning.
Right. The cured stator is then fed through a 3D automated optical inspection, or AOI system. Advanced imaging technology scans 100% of the parts, looking beneath the surface of the cured epoxy for microscopic air bubbles or voids.
Why is an air bubble trapped inside solid epoxy so dangerous? It's sealed in. What harm can it do?
Air is a terrible conductor of heat, and it has a very low dielectric strength compared to solid epoxy. If a tiny air bubble is trapped right next to a high-voltage wire, two things happen.
Okay, what's the first?
First, that specific microscopic spot on the wire cannot shed its heat into the epoxy. It becomes an insulated micro-hotspot, constantly running hotter than the rest of the wire.
And the second?
Second, the high voltage can ionize the air inside the bubble, causing a microscopic electrical discharge, known as a partial discharge or corona.
Tiny sparks happening inside the bubble.
Yes. Over thousands of hours of driving, that localized heat and those tiny sparks will aggressively break down the molecular structure of the surrounding insulation through carbon tracking. Eventually, the insulation fails, the wires touch, and you get the catastrophic interturn short circuit we discussed earlier.
So an air bubble is not a design flaw. It is a microscopic manufacturing flaw that quietly incubates into a thermal time bomb 50,000 miles down the road.
A thermal time bomb. That perfectly encapsulates why they are so meticulous with the 3D scanning. They have to find the bomb before it leaves the factory.
And speaking of meticulous, there is one final manufacturing control detailed in the blueprint that I found absolutely wild. It involves a substance called Niogel 760G and UV tracking.
Ah, yes, the application of Niogel. Even with the soft gold plating, the hyperboloid geometry, and the strain relief brackets, the engineering teams take one final chemical step to protect the connectors.
Automated robotic dispensers inject a highly precise, mathematically calculated volume of this specific grease directly into the terminal cavities just before they are mated.
Right, the specification sheet describes it as a fluorosilicone base with a copper passivator. It's a conductive anti-fretting grease.
What does that actually do?
The chemistry is very specific. The fluorosilicone base acts as a viscous dampener, physically absorbing microvibrations. The copper passivators chemically neutralize any oxidation. It acts as a final, impenetrable chemical barrier against oxygen and moisture, completely sealing the gold contact surfaces from the outside atmosphere.
But again, the PFMEA raises the critical process question. How do you guarantee the robot applied it perfectly on an assembly line moving at high speed? You can't just hope the dispenser didn't clog or misfire.
No, you can't.
So they make the grease glow in the dark.
It is a brilliant quality assurance mechanism. The anti-fretting grease is pre-mixed at the chemical supplier with a specialized UV fluorescent tracer.
So it glows under blacklight.
Exactly. After the robot injects the grease, the motor moves down the line under high-intensity ultraviolet lights. Automated, high-speed machine vision cameras inspect the glowing footprint of the grease inside the terminal.
The cameras can instantly see the exact volume and distribution based on the glow.
Right, if the algorithms determine there isn't 100% coverage, or if they detect a tiny drop of glowing grease splattered outside the designated target zone, which could attract dust and cause a short tox, the part is instantly flagged and rejected from the assembly line.
They are literally using ultraviolet lasers to check for microscopic bubbles in glowing fluorosilicone grease. The level of institutional paranoia, and I mean that as the highest compliment to the engineers, is astounding.
It is the unsung hero of automotive reliability. Process control is how you guarantee that the brilliant, five-dimensional engineering design actually exists in the messy reality of the physical world.
Okay, let's recap this incredible journey so far. The design engineers deeply understand the physics of how the wires fail. They wrote a software architecture that senses a broken wire in 2 milliseconds by watching the math breakdown.
Check and check.
They physically redesigned the metal with aerospace-grade beryllium copper, self-lubricating soft gold, and hyperboloid springs. And the manufacturing engineers built a sci-fi factory with servo robots, hard vacuums, 3D scanners, and glowing grease to put it all together perfectly.
The blueprint is fully realized.
Which brings us to the fifth and final dimension. We are at the final stage, the torture chamber.
The DVP&R Design Verification Plan and Report. This is the mass production validation phase. The engineers have designed it perfectly, and they have built the physical prototypes perfectly. Now, their sole job is to try their absolute hardest to destroy their own creation.
Let's look at the LV214 SG4 vibration and thermal test. Reading the parameters of this test, it frankly seems impossible that any physical object could survive it.
The LV214 standard is widely considered one of the most brutal, unforgiving validation protocols in the global automotive industry.
What do they do to it?
The test engineers take the fully assembled heavy traction motor and rigidly bolt it to a massive industrial shaker table. They then subject the entire unit to a 3-axis random vibration profile. They shake it violently in the X, Y, and Z directions simultaneously at dynamic frequencies ranging from a rumbling 10 Hz all the way up to a screaming 2,000 Hz.
The forces must be immense. The specs say an acceleration force of 35 meters per second squared.
They are essentially simulating the mechanical stress of driving a heavily loaded vehicle down a deeply rutted, washed-out dirt road at top speed continuously. But they don't just shake it.
Of course not.
While the motor is enduring this extreme kinetic violence, the entire shaker table is enclosed inside an environmental climate chamber. The test engineers subject the vibrating motor to severe thermal shocks, rapidly swinging the ambient temperature from a freezing negative 40 degrees Celsius up to a baking positive 150 degrees Celsius over and over again.
And how long do they do this for?
They run this combined torture test continuously for a minimum of 500 hours, Spade.
500 hours. That is nearly 3 full weeks of nonstop freezing, baking, violent shaking. How does anything complex survive that? And more importantly, what is the grading curve? Because surely, after 3 weeks of that, the connectors are allowed to degrade a little bit.
There is no grading curve. The acceptance criteria are absolute. After the 500-hour ordeal is complete, they meticulously measure the electrical contact resistance of those gold-plated hyperboloid terminals.
And what's the limit?
The electrical resistance is only allowed to increase by a maximum of 1.2 milliohms from its pre-test baseline.
1.2 milliohms. That is barely a rounding error. That is practically zero physical degradation.
The requirements were even stricter during the test itself. While the motor is being shaken and baked for 3 weeks, high-speed electrical monitors are constantly watching the continuity of the circuits.
Watching for any slips.
If there is a single intermittent break in the electrical connection, even a momentary physical separation of the pins lasting longer than 1 single microsecond, the entire design fails mass production validation.
1 microsecond. So that hyperboloid finger trap design, the beryllium copper springs, the glowing grease, this is where they prove their worth. The connection cannot let go, not even for a millionth of a second, while being actively shaken to death for 3 weeks.
It proves that the mechanical isolation and the tribology of the soft gold work flawlessly under extreme duress. And if the motor survives the 500 hours, it immediately moves to the high-voltage insulation test.
What happens in that test?
They take the battered, thermally shocked stator, hook it up to a testing rig, and blast it with 500 volts of direct current for a full 60 seconds.
They are intentionally trying to force the electricity to arc through the insulation.
Exactly. They measure the resistance of the insulation, the epoxy that was vacuum sealed and scanned for bubbles earlier. The electrical resistance of that barrier must remain greater than 100 megohms, with absolute zero leakage, current, or dielectric breakdown.
Meaning the epoxy held up.
It definitively proves that the massive thermal expansion and contraction over the 500 hours didn't create any microscopic stress cracks in the resin.
Okay, so the physical hardware passes the torture test. The metallurgy and the chemistry are indestructible. But that brings us to the ultimate simulation outlined in the source document, the HIL test. Hardware in the loop. This is where they test that 2-millisecond algorithmic reflex we discussed at the very beginning.
You cannot validate the hardware and software in isolation. You must test how they interact during a dynamic, high-stakes event. In the HIL test, they take the motor control system, the physical microcontrollers, and the inverter, and connect them to a high-fidelity, real-time mathematical test bench.
So it's a simulation.
Right. The computer simulates the physics of the motor spinning up to its absolute maximum operational limit, 12,000 RPM, operating under maximum torque load.
The exact nightmare scenario we started this deep dive with.
The precise worst-case scenario. And then, intentionally and brutally, the test engineers trigger a hard open-circuit failure in the simulation. They digitally sever the wire while the system is operating at maximum electrical and mechanical stress.
So they basically drop a digital bomb in the system at 12,000 RPM, and the software has to catch the virtual car, process the math, and stabilize the electrical grid in less time than it takes to blink.
And we get to watch the entire multi-layered safety architecture deploy in real time, captured on high-speed data loggers. The test parameters monitor every microsecond.
To see if it all worked together.
Exactly. Did the current residual check spot the mathematical deviation? Did the PI controllers hit saturation and confirm the fault? Did the overall system meet the strict FTTI deadline of 60 milliseconds?
And it checks the hardware degraded states, too. Did it execute the stepwise active short circuit fast enough to safely clamp the massive back EMF voltage below 720 volts, ensuring the virtual battery and power modules weren't destroyed?
Furthermore, if it is the high-end dual winding system we explored, the HIL test measures the agility of the redundant switch. The microcontroller must detect the failure, safely suspend the broken winding, mathematically reconfigure that broken winding into a pure back EMF search coil, and seamlessly switch to sensorless control using the healthy winding.
And it has to do all that in a flash.
It must execute that entire logical ballet in under 5 milliseconds. The physical acceptance criteria dictate that the driver should barely feel a shudder in the vehicle. The torque ripple during the switchover is strictly limited to less than 5 Newton meters of physical fluctuation.
So if the software takes 3 milliseconds instead of 2 to catch the math error,
The simulation fails. The system goes back to the software engineers.
If the voltage spikes to 730 volts instead of clamping at 720.
The hardware fails, the system is rejected. It is a stunning display of interconnected precision.
It really is.
The HAL test truly validates everything we've unpacked today. It proves the perfect split-second harmony between the advanced vector calculus in the software algorithms and the advanced material science in the physical hardware. It proves that the entire five-dimensional engineering blueprint works flawlessly as a unified shield.
It is genuinely awe-inspiring when you step back and look at the whole picture. We started this journey looking at a problem that begins with a microscopic 5-micrometer vibration, a physical movement so small you couldn't even see it with a magnifying glass.
Right.
And we explored how that tiny movement, if left unchecked, cascades into friction, rapid oxidation, micro-lightning strikes, and eventually a molten, snapped wire inside a motor spinning at terrifying speeds.
A textbook catastrophic failure cascade initiated by the smallest possible physical trigger.
But then we saw the human response to that chaos. We saw engineers fighting back with software reflexes that operate in 2 milliseconds, diagnosing a physical break by recognizing that the fundamental mathematical equations of the circuit had suddenly broken.
The doer and the checker.
Exactly. We saw motors deliberately short-circuiting themselves at highway speeds, intentionally trapping explosive electrical energy inside a magnetic cage just to protect the battery and save the vehicle.
The brilliant paradox of achieving ultimate safety by commanding a short circuit.
We explored the incredible physical redesigns, the transition to aerospace-grade beryllium copper, the application of self-lubricating noble soft gold, and those hyperboloid connections that grip like a woven finger trap to maintain perfect contact no matter how violent the vibration gets.
Pure material science.
And we walked through the hyper-controlled assembly lines with their closed-loop servo-robotic screwdrivers tracking microscopic thread friction, the vacuum-sealed epoxies being scanned by 3D lasers, and glowing UV-traced anti-fretting grease. All of it culminating in a 500-hour torture chamber that demands absolute, unwavering perfection.
And yet, as comprehensive, robust, and brilliant as this current blueprint is, the very end of our source material points toward an evolution that is even more profound.
Oh, really? Where is this all heading?
There is a final detail noted regarding the immediate future of this engineering space. The top engineering teams are now utilizing highly advanced Python simulation tools and machine learning to calculate the precise back EMF dynamics, thermal loads, and torque ripples for these systems entirely in virtual environments.
Wait, entirely virtual?
Yes. They're creating perfect digital twins of the motors, feeding massive data sets back into the control algorithms to train them before a single physical prototype is ever machined.
So they are artificially simulating the failures, the micro-arcing, and the temperature spikes digitally. They are breaking the motor in the matrix before they ever try to break it in the physical torture chamber.
That is the trajectory. And this raises an important question, a provocative thought for us to consider as we wrap up this analysis.
Let's hear it.
As these digital twins and software simulations become infinitely precise, as we gain the computational power to model every single micromillimeter of vibration, every minute fluctuation in heat, every potential plasma microarc in a hyper-realistic virtual environment, are we rapidly approaching a threshold where mechanical hardware will never actually fail in the real world?
Wow.
Are we moving toward a reality where artificial intelligence and advanced digital modeling have already simulated, anticipated, and elegantly designed out every possible microscopic fracture, centuries of simulated time before the physical car is even assembled on the factory floor?
That is a staggering thought to ponder. A future where the catastrophic snap of a wire at 12,000 RPM isn't just expertly mitigated in 2 milliseconds, but is literally mathematically impossible because it was erased in a digital simulation years before the car existed.
It changes everything.
It really makes you realize that the vehicles we drive aren't just mechanical machines. They are physical manifestations of some of the most complex, rigorous, and forward-thinking problem-solving on the planet. I want to thank you, the listener, for joining us on this incredibly deep technical dive today.
It was a great discussion.
The next time you are cruising down the highway, maybe listening to music or just enjoying the drive, and you press that accelerator, take a brief moment to think about the invisible, microscopic war zone happening beneath you. Think about the brilliant, invisible engineering working silently in the milliseconds to keep you moving forward safely. Keep wondering, keep exploring, and we will see you on the next deep dive.